To continue our discussion of the Lorentz transformation and relativistic effects, we consider a famous so-called paradox of Peter and Paul, who were supposed to be twins born at the same time. When they are old enough to drive a spaceship, Paul flies away at very high speed. Because Peter, who is left on the ground, sees Paul going so fast, all the Paul's clocks appear to go slower. His heartbeats go slower. His thoughts go slower. Everything goes slower from Peter's point of view. Of course, Paul notices nothing unusual, but if he travels around and about for a while and then comes back, he will be younger than Peter, the man on the ground. That is actually right. It is one of the consequences of the theory of relativity which has been clearly demonstrated. Just as the mu mesons last longer when they are moving, so also will Paul last longer when he is moving. This is called a paradox only by the people who believe that the principle of relativity means that all motion is relative. They say, hey, 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 from the point of view of Paul. Can't we say that Peter was moving and should therefore appear to age more slowly? By symmetry, the only possible result is that both should be the same age when they meet. But in order for them to come back together and make the comparison, Paul must either stop at the end of the trip and make a comparison of clocks, or more simply, he has to come back, and the one who comes back must be the man who was moving. And he knows this because he had to turn around. When he turned around, all kinds of unusual things happened in the spaceship. The rockets went off, things jammed up against one wall, and so on, while Peter felt nothing. So, the way to state the rule is to say that the man who has felt the accelerations, who has been things fall against the walls, and so on, is the only who would be the younger. That is the difference between them in an absolute sense, and it is certainly correct. When we discussed the fact that moving mu mesons live longer, we used as an example their straight line motion in the atmosphere. But we can also make mu mesons in a laboratory and cause them to go in a curve with a magnet, and even under this accelerated motion, they last exactly as much longer as they do when they are moving in a straight line. Although no one has arranged an experiment explicitly so that we can get rid of the paradox, one could compare a mu meson which is left standing with one that had gone around a complete circle, and it would surely be found that the one that went around the circle lasted longer. Although we have not actually carried out an experiment using a complete circle, it is really not necessary, of course, because everything fits together all right. This may not satisfy those who insist that every single fact be demonstrated directly, but we confidently predict the result of the experiment in which Paul goes in a complete circle.